the coursework, do you think that would be possible to do that?
Yeah.
Thank you.
Sorry? Yeah, you are. Okay, we'll start now. Okay, we'll start now. So today we are going to look at stresses in beams. So we have looked at trusses, equilibrium, from then we moved on to truss. Truss carries members, the forces in axial directions, either in tension or compressions. Then we looked at bending and shear. Now, all of those we looked at before to calculate or to see what are the effect of the loads in terms of the stress resultant. But how the stresses are inside the member, and particularly due to bending, that we are going to look at today, means how to calculate those bending stresses. And on Monday we looked at material property, particularly properties like yield strength. So whether we can then, if we can find out the stresses due to bending or shear or axial force, and then we can compare the load carrying capacity of the member. So what I am saying is, if I have got a member like this and I put an axial force to it, a compression, and then I know the yield strength of materials of this foam, then I can find out how much compressive force I can provide, provided I know the stress due to axial force. Similarly for shear forces and similarly for bending. Now, I'm going to introduce you the bending today, and bending is quite a significant stress for beam-like structure. Now, what I'm going to do is first demonstrate the way that we did few weeks before. So imagine you have got this beam and we are creating a bending to this beam. So one of the assumptions we will take, which is not a bad assumption so to speak, is plane section remains plane before and after bending. So what do we mean by that is, if we consider, so this is the beam, and if we consider two cross sections nearby to each other, so one is shown by, I put two pens onto them, one is green and one is blue. So that goes, so if you think about those cross section, if we cut along those pens, that will expose the cross section here. Let's say that's blue. And if I cut along this pen, then that would be it will expose the cross section, and cross section is rectangular in this case for this beam. So if I create bending of this beam, so if I bend this beam, then you could see that the cross section which is along the line of the pen remains straight. So the cross section remains straight. Before bending it was straight, and even after bending it was straight as well. Now that is one of the assumptions, it's very, very good assumption that we need to take, and that is the first assumption that we take. Plane sections remain plane. So this means a plane cross section through an unbent beam remains plane after the beam is bent. The key to much of this. Second assumption will take material properties linear elastic, so therefore characterized by one number which is Young's modulus. Deflection is small comparison to beam's length, and beam carries bending moment and possibly shear force but no axial force. So let's look at how can I calculate the bending stress if I apply a bending moment to it. So if I apply a bending moment like this, so things bend, then the stresses are generated in this beam. So our idea is to calculate those stresses. So the approach we will take is as follows. So if I put a moment like this, if I bend, then I could see the deformation is quite significantly different in different part of the beam. So compare as before, say this is the length between this cross section, or the gap between this cross section. Before bending, it's fairly the similar values. So if I take up a ruler, so they are approximately 4.5 centimeter apart. Okay, 4.5 centimeter at there, 4.5 centimeter at the bottom as well. Now if I bend them, then the top part extends, and if I measure this curved length, that would possibly be near about 4.5 centimeter, and the bottom bit contracts. So this contraction and expansion happens in the direction of the length. So the stress must be generating in the directions of the length due to bending. So that's the first thing. So the first thing to note that during bending, the stresses will be generated, and stresses would be in the directions of the length, because that's where the extension and contractions are being generated. And also we see that at the middle plane, so at the mid part of the beam, it does not change. So most likely there will be no stress along this length at all due to bending. If I bend in this way, then top part extends, so top part will have a tensile stress and bottom part compresses, so this will have compressive stress. And also we could say that from the midpoint, from this point onwards, if we go further up, the gap between those increases. That means the stresses extension increases to the top. Similarly, from the midpoint, if I come down, the contractions increases further and further, so it's getting compressed more and more. So the stress would be 0 at the middle, and it will start to increase, becoming tensile as you go up, and it will becoming compressive as you go down if you bend in this way. If you bend the opposite way, then exactly similar thing happens, but in the opposite nature. Things that were in compression becomes tension, tension becoming compression. So how do I find out what is the stress? The way we'll derive this stress is, we'll apply a moment and find out actually how much it is stretching or how much it is contracting. And if we know the stretch, then we can find the strain, because the stretch elongation divided by original length. So if this was originally 4.5 centimeter apart, now if I bend it in that manner, and now the gap is quite a lot, say maybe about 6 centimeter, so 1.5 centimeter is increased over an original length of 4.5 centimeter. So I can find out the strain. So strain is elongation over the original length. If I know the strain, I can use Hooke's law or Young's modulus to calculate the stress. Strain times the Young modulus would be the stress. So that's the approach we will be taking. So the approach is, apply a moment, find out how much has extended each part, and from that extension or elongations, you can find out what would be the strain. And once you know the stress, find out what would be the stress. And we start with this part, middle part, because that's where there is no stretching or contraction or compression. So this would be our so-called neutral axis. So that's the approach we'll be taking. So I'm going back to the notes now. So this is in the lecture note. So exactly my beam here, and it has been bent in that way. And then what we need to find out is what would be the stresses. So now if I draw them a little bit bigger, these are the stresses that we will get. So if I take two bars at a distance dx apart, dx is the small distance apart, very much like the gap between those two pencil mark primarily, that's our dx here. And if I bend it with some bending moment applied in the end with m, then it will bend in this way. And it will bend to a radius of curvature r. That means if you put a perpendicular line through here, perpendicular line through there, it will meet up at an imaginary point here, which you could also see it in our model beam case as well. So in our model beam case, if I bend it, you could see possibly at some point down there, these two lines will meet. So that would be our center of curvature. Okay, so where these two lines meet, That would be our center of curvature. So this is our center of curvature. And until the midpoint is our radius of curvature. R is the radius of curvature. So if this angle is made is theta, between these two after bending is theta, then this distance you can relate that to R is up to that point. So this distance which is does not change, so dx is equal to R times theta. Okay, dx is R times theta. So it's same as like you calculate for an arc of a circle, the radius times the angle that it subtends in the center is the circumferential distance or the arc distance. So this dx is R times theta. Now if we want to find out what would be the extension at a distance y from the middle point. So if you go at a distance y from the midpoint, if we go at a distance y from the midpoint upwards, what would be its extension? So that y is at a distance here, so that would probably be somewhere here. So what would be the extended length? That's what we need to find out. Now of course up to that point what would be my radius? So if this is y, so this length would be R plus y times theta, because the radius now would be R plus y. So this green line is R plus y times theta. So if this green line is R plus y times theta, I can put back the value of theta from here. So theta from this part, I can say theta is dx over R. So I can put it back here, the theta. So this is R plus y times dx over R. Or I can put this a bit of algebra I can do, 1 plus y over R times dx. So this green line length is 1 plus y over R times dx. So how much this has extended then? So the actual extension then we can calculate as that original length was dx. So the extension in this case then, extension would be that this green line length, which is 1 plus y over R times dx minus the original length that was dx apart. So if we do that calculation, so dx plus y over R, so extension is actually y over R times dx. So this green line is extending by this much amount. Now what we can say it from here? These are of three things, y, R and dx. So dx is, use it from calculus. Why? Because that's an infinite similar length that could be as small as we'd like, so that things don't vary over that small distance. So you can take it as 1 millimeter, 0.1 millimeter, a nanometer dx could be, depending on the scale that you are choosing, for example. So dx could be as small as possible, so as you are satisfied that over that length things like bending moment and the other things don't, or the load, or the variations are not unknown. So you can know that variations, for example. So this is the extension. It also depends on y. So that means if you go up from this point, if y is more, extension is more. So that we could see from our demonstration, that if we go from the central plane as up and up, our extension will increase. And what about R? So R is the radius of curvature. That means if we bend it to a light curvature like this, that we apply less moment, then our extension is low. So less bent means radius of curvature is very high. But if I bend it too vigorously, that means my radius of curvature would be much more tight, much more small. So R is small compared to this R. So this is little bent, so R is big. So radius of curvature is big. So when I bend it much further, much more vigorously, radius of curvature is small. So flat line of course has got a radius of curvature of infinity. So these two lines would meet at infinity. So that makes sense as well, that if the radius of curvature is big, I have got higher extension as you go up. And if radius of curvature is small, I'll have less extension. So that's the extension. Now how can I find out the strain? So the strain I'll find out by dividing extension over the original length. So extension over the original length. So that would be the strain. Now another thing which I should have said it here, y, if it is negative, if you start y to come down, that would be with a negative sign. So that means it is a compressive extension or compression, for example. So the stress would be appropriately compressive. So the strain is extension over original length. So what is the extension? Y over r times dx. Over the original length was dx. So the strain is y over r. And with a symbol of strain, this is the Greek epsilon, that's the strain. So the stress, our much more desirable quantity, the stress, that's what we want. Stress is given by sigma is E times epsilon. E is the Young's modulus and epsilon is the strain. So the stress is EY over R. So this is stress. So we now have the stress. So we know if you apply to a bending moment, then you will have this much of stress, which will depend on the Young's modulus of the materials, depends on where you are measuring the stress, because the stress would be increasing as you go away from the middle plane. So from the middle plane, if you go up, you will start going upwards, you will increase stress, and if you come down, it will also start to increase stress. And it's related with R, which is the radius of curvature. But the whole thing, you might say, I don't know what R is. You don't expect me to take a ruler and make what is an R if I apply. I know what bending moment I have, what moment I have applied to my beam. This much I know. I don't know what is R. I know, of course, E, but R I don't know, of course. Otherwise, if I don't measure it, I don't know what it is. So that means I can only do it by experiment. How this R relates to the M, for example. If I can find that, if R is related to M, I can find how R is related to M, then that will solve my problem. Then if a moment is given, I can quickly find out what would be the stress. So how can I find out that R and M relationship? Well, I know the stress, and this stress is at a distance y. So if I take a small area of a cross section, so this is the cross section of the beam, rectangular cross section of dimension B and H. So if I take a small area over here, the stress in that small fiber is EY over R, which we are saying it here. So what would be the little force? So the stress is acting perpendicular to that area. So the little force should be, so we can call it dF into that area. So dF would be stress times the area. So stress is EY over R times the area of that small fabric. So that is B times dy. So B times dy is this small area. Dy is the depth along if I go small area above the height. So that is the force that is acting into this due to bending. So just before you don't get confused, so what we have done is we have found an expression of stress at a location y from the neutral axis if I applied a bending moment. Now the expression I have got within some symbol of R, that I need to measure the radius of curvature, that how that beam has bent, so that I need to find out that. Now my objective now is to relate somehow that R to my applied moment. So that is my objective. So that's what I am trying to do. So I am saying that this stress, if it applied over at that level, then I can take a small strip of area, B times dy. So the stress I can convert to force, that stress times the area. So this is the stress. stress times the area would give me the force. So once I know these two, then I can say, okay, this is the force. Now what is the moment? Moment due to that force about this axis would be the distance times the force. So dF times y. So this force is acting perpendicular to the cross section. So the distance is to that force is y. So dF times y is the moment about this axis. So let's do that one. So multiply that with y. So I'll get Ey over r times b times dy times y. Okay, so I could multiply y together. So I could get Ey square over r times b times dy. So that's a moment due to this little force over the small area. What about the total moment then? So the total moment would be, if I sum it up and do these things for all the little area. So I can take another area over here. I can take another area over there, for example. So if I divide my cross section into this so many little things, and then so varying dy over the whole depth, then I'll get the total moment. So the total moment I'll be having is integration of this little moment. So the integration of little moment is here, Ey square over r times b times dy, and this would vary from, y would vary from minus h over 2 to plus h over 2. So E is materials constant, so I can take it outside the integration sign. That doesn't depend on E, so I can take it out as outside. B is, for this cross section, is constant. If B was not constant, if it was another triangular or a circular cross section, then you need to integrate with it. Now that's constant, so I can take it outside the integral sign. Then of course r is the radius is fixed for this beam. I can take that one outside as well. So this is then becomes h over 2 to plus h over 2 y square dy. So if you do that integration, that would give you y cube over 3. And y cube over 3, if you put h over 2 over minus h over 2, then you get this formula. So it would be y cube over 3 is the integration, and limit is h over 2 and minus h over 2. So that would be h over 2 cube, which is h cube over 8, 24, minus of 24. So that would give you EB over R times h cube over 12. Thank you. So this is my moment. So the moment I am getting is equal to E over R times BH cube over 12. Now this thing is particularly important thing. This is related to the properties of the cross section. This thing is called second moment of area. Second moment of area, and usually given by this letter I. So that is the symbol that we use. For a rectangular cross section, it is BH cube over 12. So the moment and the radius of curvature that we have done is, moment is EI over R. So this is how they are related. Remember, go back there, E over R is sigma over Y here. So if I rewrite that expression over here, so if I take another piece of paper and try to write this. So from these expressions, I could express that as sigma over Y is equal to E over R. So sigma over Y is equal to, now know what is sigma? Sigma is the stress due to bending. So sigma is the bending stress. What is y? Y is the distance where you are measuring the stress, distance from the mid plane where you are estimating the stress. What is E? E is Young's modulus of elasticity. So this is the material property. Young's modulus of elasticity. So that's the formula. And then we know, we have gone it here as well. This is equal to E over R is same as M over I. So from this expression we can say E over R is M over I. So that is the expressions of bending you can use in any combination. So what is M? M is moment applied to the beam, moment applied to the end of the beam. And what is I? I is a property of the cross section, property of the cross section geometry. And in this case, I is called second moment of area. Why they are called second moment? We'll come to that later. But it is particularly this y square, that is the second moment. But why it is a moment and things that will come later, what we'll do. So this is the formula that you need to know. Sigma over y equal, so if for a beam, you know the bending moment is given and cross-sectional property is given, then you want to know the stress, you use this expression, sigma over y is equal to m over I. So you can forget about the middle bit. So you can forget about the middle bit and then you can calculate the stress at a point if you know the bending moment. Or if you know the bending moment at any location, then and at y is the location from the mid plane going up or going down, and I is the property of the cross section. So that's all really that we have to do. So just to summarize, what we have done was that we started off by saying, taking some assumptions about how things would bend if we apply a moment. And from the bending, we calculated extension and elongations. From there, the strain. And from the strain, we got the stress. From the stress, then we relate that to the force and calculated the moment and ultimately the moment applied. And this relationship linked the radius of curvature to the moment. And we'll be using these expressions later when we calculate the deflection of beam. So this is quite an important expression as well. So in general, if a single formula for bending that you need to know or remember, this is it. And in fact, even you can forget for the time being this bit. So this is the part, sigma over y is equal to m over I. So let's do an example and then see how all of these things fit in and applies to. So we have got an example here in your lecture note, and it says a beam of rectangular solid section, so rectangular solid sections like this, with cross section 80 millimeter by 30 millimeter. So this is 30 millimeter and that is 80 millimeter. Has a yield stress of 375 MPa. That means somebody may have done a test of this material and they have found that the material property, if they have done a test, so this is the stress, this is the stress versus strain of the material, and they have found something like this maybe that have happened. So this value is 375 megapascal. So this is the material. So 375 megapascal is your yield strength. So yield strength is sigma y is 375 megapascal for this beam. So what you have to do is calculate what is the largest bending moment that this beam can resist. If all the material must remain elastic when it is bent about it, if the stronger axis. So let's do this calculation. So you have got a beam of 80 millimeter by 30 millimeter. 30 millimeter by 80 millimeter. So question is, what is the maximum bending moment this can take? Now we know this formula that we have just derived. Sigma over y is equal to m over I. So we'll be using that expression. That moment capacity is m and I, so I'll be using that expression. Sigma over y is equal to m over I, or moment capacity that we want to know. So the moment capacity m, if I rearrange this, it will be sigma times I over y. So this is the moment capacity, it would be sigma times I over y. So let's find out each of these one by one. So what is the value of sigma? Now sigma value here is the maximum that I can have. So the maximum stress that I could have from bending of this material is 375 megapascal. That is the maximum I can have. So that will give me the maximum moment. So if I give less moment capacity means less sigma. So if I increase the moment further and further, my maximum value I can go up to is 375 megapascal. Now in terms of the unit, I will use Newton and millimeter. So these are the two units that I will use. So megapascal means what? Megapascal means 375 times 10 to the power 6 Pascal. Now 1 Pascal is Newton per meter square. So that means this is also 375 Newton per millimeter square. So Pascal is Newton per meter square. So 10 to the power 6, if we convert that to Newton per millimeter square, so megapascal means same as Newton per millimeter square. So 375 megapascal is 375 millimeter. So what about I, second moment of area? Second moment of area about this axis is, we just calculated for a rectangular section, it is BH cube over 12. So B is the width, H is the height, and cube over 12. So we'll use that. I is BH cube over 12. So B is 30 millimeter here. Be careful to choose which one is B and which one is height. And 80 to the power 3 over 12. And unit would be millimeter to the power 4. So if I do the calculations, that would give me so 30 times 80 to the power. So I get 1.28 times 10 to the power 6 millimeter to the power 4. Now what would be the y, you think? What should be the value of y that we will take? What should be the y? If somebody can tell me what is y, we should take it here for maximum bending moment, then they have understood it. Half of the height, you mean? Is that okay for everybody? Half of the height. Because here bending stress is 0. So if I plot the bending stress, sigma, here the bending stress is 0. If I go up, it will increase. So maybe this is the maximum tensile. And if I come down, it would be compressive, like this. So this would be maximum compressive. So the maximum stress would be either at the top or at the bottom. So to calculate maximum capacity, I am comparing the maximum load carrying capacity, maximum the moment carrying capacity. So we should compare that wherever the stress is getting maximum due to bending. So this is either that location or that location. So how much is this? So y is the distance from the mid plane, so that is 40 millimeter. So y is 40 millimeter. So if I put that back now, everything together, so m is equal to sigma, which is 375, times I, which is 1.28 times 10 to the power 6, divided by y, which is 40, that much of Newton millimeter. So if I do the calculations, divided by 40 times 375. So that gives me this much, 12 times 10 to the power 6 Newton millimeter. And if you want to do it in a different unit, you could say 12 kilonewton and meter. So that is the moment at which the beam will reach its maximum capacity if it is bent in that configuration. If it is bent in this configuration though, then there would be different I. I about bending is about that axis then. So you need to calculate then I would be not 30 times 80 cube over 12. It would be then 80 times 30 cube over 12. So that would have less capacity because the second moment of area would be lower about that axis, about this axis, rather than that axis. So these are called major and minor axis. So the major axis is, so if you have got, let's say, this cross section, I'm drawing it a little bit bigger. So imagine this is 80 millimeter. This is 80 millimeter. And this is 30 millimeter. 30 millimeter. Now, if the bending happens about this axis, about this horizontal axis, let's say I call it as axis 1. So I about axis 1 is equal to 30 times 80 cube over 12. So that much millimeter to the power 4, and that is what we have calculated is 1.828 times 10 to the power 6 millimeter to the power 4. But what about if we calculate this I about this axis? This is also a symmetric axis about these two. So I about the second axis would be, now you have to consider the rectangle now in this way. So that would be 80 times 30 cube over 4. So that's what we have to do. So that is 80 times 30 cube over 12. So if I do that calculation, that would be 0.18 times 10 to the power 6 millimeter to the power. So you can see here that I22 is less than I11. So I22, this is called a minor axis. And this is called a major axis. So the axis about which second moment of area is high, then that's called major axis. So axis about which the depth is bigger for a rectangular cross section. Now of course if it is fully symmetric like a circle or square, then major and minor axis is less meaningful. But many more standard axes you will have a major and a minor axis. So if it bends in this way about that axis, then it would have a less moment capacity because the I value would be lower. So it will reach the yield strength or the capacity strength much quicker if it is bent about this vertical axis. So if it is bent about this vertical axis, that means if I bent it that way. Whereas if I bent about the horizontal axis, so in other words, if I bent it in this direction, about that horizontal axis, then it will take higher amount of moment. So this is all there is to bending stresses. So the lower second moment of area is minor axis and higher second moment of area is major axis. Now how do we get that? For rectangular cross section I have just shown you, but that's the subject matter for our last topic. So we'll go into detail about this major and minor axis in the last section. Okay? So that we'll do in the last couple of lectures. Any other question? So just couple of points really. In terms of assessment, there would be, for the last quiz, there would be the solution which I haven't discussed, but there is a short video of that solution. So you can watch that video, okay? Solution for quiz 2 that you could watch, and then if there is anything that you need to be remarked, so please do so. Thank you. Yeah.
I just had a question.
Yeah?
I understood everything there.
Good.
I just wanted to ask a question about last week's topic.
Yeah.
Because I was doing the tutorial read.
Yeah.
And I just wanted to ask how would you calculate the magnitude of the bending moment, as well as how would you draw it? Because I drew the shear force diagram, but how would I draw the bending moment diagram for this curve?
So have you taken into the sign properly? Let's see. So the load, so the sign convention is this, right? Sign convention is, this is a positive load.
Yeah.
And then this is a positive shear force.
Yeah.
And this is a positive moment, right?
Yeah.
So this is a positive load, means this is negative. So you start with a negative and then positive load, and this is with an decreasing value.
Yeah.
So that is reducing, that's great.
Yeah.
And then there is nothing and up till comes, that's very good.
Yeah.
Now this bending moment would start at a very high negative slope, so that means something like that. Okay?
Yeah.
And then it will come to a zero slope at this point.
Okay.
So you could say something like this. Okay?
Okay.
And then it will increase to a positive slope up to this point. So let me do it a little bit bigger. So here is the eraser button.
I know as you can just erase that. If you want to zoom in, you can just zoom in.
So then what will happen is, if you do it,
Oh, sorry. You can just erase that one, and if you don't
undo. Okay, so what I'm saying, let me draw on my piece of paper.
Sorry.
So what will happen is, so from here the bending moment will come like this, so that is a zero force there, and then from here that will start to increase. It will start to increase, and then from there in the end until the final point is a constant slope, because that's
Okay. So how would you calculate the magnitude of the maximum bending moment?
So the here is what you have to do is the area of that, or what you can do is you can take a section that point.
Yeah.
So you calculate the moment due to this,
Yeah.
and moment due to this a trapezoidal segment of the load.
Yeah.
So trapezoidal segment of the load, what you can do is you can find out what is this much, what is that much, and then what you need to do is you can make it like a two triangle.
Okay, and then you can find the area.
Yeah, so you can find this area, it will act at that point, and this area as a triangular load, it will act at that point.
Okay. Okay, yeah, that makes sense.
Yeah.
Thank you, sir.
So can you upload the lecture notes for this class, because they weren't up on? Like,
Yeah, this is there.
Is it there? So because I couldn't find it. Is it? Okay.
But not in like the normal week.
It's not in the weeks.
It's not this week.
Yeah. Okay.
It's in Oh, it's in the revision. Sorry, it's not in the week one. Yeah, I'll upload that in the week one. Sorry about that. Yeah.
I'm not here for the test next week.
Mitigating circumstances.
Yeah, how do I do that?
So you remember the last test?
You said something about.
The form. There is a form
Yeah,
there.
I just couldn't find it.
So if you can send me an email, because do you have the email that I sent with the announcing the last test?
Yeah.
Yeah. So in there is a web address.
Okay, perfect.
Yeah. So click on that web address.
Yeah.
It will take you to, and then you fill in that form.
Okay,
Yeah.
thank you.
And then what happens is the committee will look at it, and then they will say, okay, you would be assessed for 90%.
Yeah,
rather
so is
than,
it 0.9 times whatever I get?
Yeah. So not 0.9 times. So that test would be then ignored for. So of course depends on the committee what they say. But if they approve your mitigating circumstances, let's say, then what will happen? They'll say that we'll ignore your marks for that test, and then you are assessed on the rest 90%. Rather than you getting 0 out of 10.
Yeah, okay.
So, but that committee has to approve your case. So, put in evidence or whatever that is required.
Could you take some pictures of your notes, please?
Do you think these are useful for you so that I could scan it and put them in back?
Yeah, I think that would be very useful.
These are useful.
Excuse me, sir.
Yes, sir.
How to draw the
Thank you.
draw the red, green.
So this is the CR4. So that goes in a pair.
How to draw it? For example, this diagram.
So if you look at it,
Yes.
so the CR4 on the left hand side is the load, right? So that the load is going up. So the load is going up means it's the downward CR4, you know. So that load is vertically downward is a positive one.
Positive one.
So this is going up.
Yes. It
So that
should
means
be
negative.
Negative.
Yeah, so you start with the negative.
Oh, so the green are usually the. Oh, okay.
Got it?
Yes, got it. Thank you.
Mr. I have a question.
Yeah?
Like when we take this bridge,
Yeah?
if we were to do a bridge analysis for this, or like maybe a car of 1.2 kilometers or something like that, is going to go through it. How do we like visualize that force? Will it be a uniform
It could
load?
be anywhere. So those are if a car or a vehicle goes through there, then you may need to take that load could be anywhere. It could be here, then of course that goes directly to the support, or it could be here.
So we take it at different locations to
Different
determine-
location. So
Okay.
in this case, you just take 2 locations. That would be enough because these 2 would be symmetric. So if you analyze that load to put on B and do an analysis,
So-
then you put on C and do an analysis. So C would be critical possibly.
Would we take like the loads at each tire, or we'll just take it at the center of gravity?
Depends on how big is your truck. If the truck is as big as the truss, then that is different. If this truss is big compared to the truck, then you could take off that as a load. But if you say, okay, my one wheel could be there, another wheel could be there, then this is what you need to take. One load there, one load there. One load there, one load there, for example, in another situation.
So we just divide.
You
like, the
just
total
see
load by
what is
4.
going to be the worst case scenario.
Oh, okay.
So that will depend on your truck dimension.
Thank you.
Sorry, I was just going to ask you, to do with the coursework, our group was thinking of doing like a section of like a roller coaster. And we were wondering, as long as we're inspired by like a roller coaster in real life, would we be able to almost create our own just
Yeah,
model of it, so
yeah,
we can
yeah.
sort of determine the angles and know what they are exactly,
Yeah.
instead of guessing what it might be?